everything we've talked about so far, Newton's second law, F equals ma, our momentum, our energy, all of that is still perfectly valid, but it only describes the motion of the center of mass of our object. Okay? For example, I know if I take a ball and I throw it, it follows a nice parabolic shape. If I were to take a hammer and throw it, well, first of all, it would rotate head over tail. But if you were to watch the center of mass, it would follow a nice parabolic trajectory, just like a ball would. So everything we've talked about is still valid, but it only describes what's happening to the center of mass of your object. So we need to talk about center of mass for a minute here. An object that's uniform, symmetric in all directions, the mass is evenly distributed, the center of mass of such an object would be smack dab in its geometric center. So the center of mass of a meter stick is in its center. Okay? The center of mass of my cylinder here is in the center. It will be in the geometric center. So halfway between here and here, and then halfway between here and here, halfway between here and here. So right smack dab in the center. Center of mass of the hoop is also smack dab in the center. The center of mass does not have to lie on the actual physical material of the object. The center of mass, right in here, is still in the geometric center, even though there's no physical material in there for it to reside on. Okay? Now, the center of mass doesn't necessarily mean that there's equal amounts of mass on both sides. So if we took this hoop and cut it through its center, we'd have two pieces. Both would have the same mass, and that's because the mass was distributed evenly. What the center of mass does represent is a place where your object will be balanced. If you support an object so that its center of mass is above the base that it's sitting on, then your object will be supported and it will not turn, it won't rotate, it won't fall over. I can do it this way, I can do it this way. As long as the center of mass is above my hand, the base, then it will stay balanced. Now, you've probably had a little experience with that. If you've ever ridden the bus or a train when you had to stand, did you stand with your feet nice and close together? No, you usually put your feet out. That provides a bigger base. Everywhere between your feet is your base. As long as your center of mass is above that base, then you're balanced. You're not going to fall over. If you lean too far forward or to the side, such that your center of mass moves over from above your base, then you will fall. You'll start to tip over. And that's what happens to semi-trucks, for example. When they're driving along, if they're going too fast, their inertia makes them start to tip. As soon as the center of mass of the truck is no longer over the wheel, it falls. And that's why, like going from I-80 to 6 South, I don't know if you've noticed, there's big, humongous signs that tell you to slow down. The signs got bigger and bigger over the years. It used to be one of those normal little orange signs that was, warning 30 miles per hour or whatever. But then the signs kept getting bigger and bigger because people weren't paying attention. They weren't slowing down. And trucks were rolling all the time. Okay. Now, an object where the mass is not uniformly distributed, for example, a hammer. To find the center of mass, it's really actually easy to do experimentally. Not only is an object balanced if the center of mass is over the base, if allowed to fall, for example, here with a meter stick, if you allow it to fall and come to rest, it will come to rest so the center of mass is below where you're holding it, so that it's below the rotation axis. So, for example, my hammer here, if I let the hammer fall and come to rest, the center of mass lies somewhere along this line under my fingers. If I hold it at a different location and let it fall and come to rest, the center of mass is somewhere right below my fingers. So the center of mass of this hammer is right there. Right in that location. Now that doesn't mean, if I, for example, didn't care about this hammer and I brought a saw in and cut it right through the center of mass, I would have the head in one hand and the handle in the other. Would they have the same mass? No, the head is much heavier than the handle is. So center of mass does not necessarily mean equal mass on both sides. It means that it's balanced if you support it there. What it really boils down to is an equal torque on both sides. And we're going to talk about torque a bit. Okay? To find the center of mass of an object that is not geometrically obvious, you actually have to integrate. So, for example, if you have an object, let's say we have an object like this. If you want to find the center of mass of an object, technically, you need to find the center of mass of its x on the x Cartesian coordinate system. You need to find the y center of mass and the z center of mass in order to accurately describe where each of them is. The equation . 1 over the total mass of the object times the integral of the position. So this x represents how far each little piece of mass is from the origin you've chosen. So basically, you have to break it up into a bunch of little teeny tiny masses, little infinitesimally small masses, little dm's, and you need to integrate those masses according to where and how far away they are from your x-axis. Okay. And the same or similar is true for the y-axis and the z-axis. Now dm you have to write in terms of dx and dy and dz so that you can figure out where everything is located. And you would do that by way of density. For those of you in Calc 2, you may probably see these type of problems where you're finding the center of mass of objects. The nice thing is, too, though, something like this. Now, I tried to draw this uniform. I didn't do a very good job. I'm sorry. This is 2. This is 2. You can simplify this equation down in some cases. This would be a case where we could. Remember, the integral is simply the summation of a whole bunch of little pieces. If you only have a couple pieces that you need to add together, you can take simply their masses times their distances over the total mass and still get the same result. That's all the integral is doing. It's a summation, but it's a summation of a whole bunch of pieces. If you can break your object down so that it's only a few pieces, you can simply take their distances times their masses and add them together and divide by total mass. This works for the y direction. And z direction as well. So here, for our object, we could treat this as if it were just two rectangles. Where would the center of mass of a rectangle be? In its center. Yeah, we're assuming it's uniform. So we could actually treat this as if it were two pieces of mass. And use this, just the x1 m1 plus x2 m2 over m to find the x center of mass. So the same for y. Z, I haven't drawn this three-dimensionally, assuming it has a uniform thickness in the z direction. This will be in the smack dab center between the thicknesses. Okay. So let's find it for this. Let's say this has a total mass m.
Draw that at an angle.
I'm sorry, what?
You have two similar sized blocks there.
They're two blocks, they're not the same size.
Right. Okay.
That's fine.
So you could just do this so they were exactly both the same size and the same.
But then finding this geometric center is going to be harder.
That'd be more math.
So it's easier if I treat them as a rectangle, then I know where the exact center is. Drawing them this way, we're going to have to figure out how much mass both of them have.